Welcome back to our cosmic journey. And I'm really excited to meet with each and every one of you this week as you're here as we launch into another module focused on astral phenomena, where we'll uncover the science behind the stars that light up our night sky. Did you know everything about the stars and what stories they tell, how they're born, what they're made of, how far away they are, and how long they live, and even how they die? It comes from decoding hidden messages, scientific data hidden within their light spectrum. Every photon that reaches the Earth carries clues about the universe's deep history. But to understand these questions, we first have to ask ourselves, what questions should we be asking? And how do we find the answers? And that is where a scientific inquiry based investigation utilizing evidence will come into play. When we look up at the night sky for a moment, just as like what we're doing right now, notice on how not all the stars shine equally as bright. Some glow white or even blue, others burn orange or red. These differences, again, tell us stories about their temperature, their mass, and how much energy they are currently producing using chemical reactions on their surface. And here's the coolest part. In our solar system, our sun is a garden variety star. So the same techniques we use to study the sun, like spectroscopy, is important for us to be able to learn more about. Because spectroscopy is just breaking down the light into components or wavelengths that unlock the secrets of our distant stars. And by studying starlight, we can begin to answer some of the huge questions that cosmologists and astronomers study. Questions like, how do stars form? How long do they survive? And what is their ultimate fate in the night sky? These are the mysteries we explore together in this module dealing with astral phenomena, a field that sits right at the intersection between observation, physical science concepts that we have already covered in thematic sections 1 and 2, but also our own imagination to be able to tell the story from the human perspective. Now, before we get into these stories of starlight and delve into modern astrophysics, let's rewind a few centuries and look at the historical implications of how we came to be able to acknowledge astral phenomena. Because our understanding of celestial behavior really wouldn't exist without early astronomers like Tycho Brahe and Johann Kepler. Brahe, long before telescopes were invented, spent decades charting the stars and the planets with rather remarkable precision for his time. His data became the foundation of his student and actually employee, Johann Kepler, who eventually developed the three laws of planetary motion. You see, Kepler discovered that planets move in ellipses, not perfect circles like previously thought, and that they sped up where they're closest to the sun due to the influence of, say, mass. And that the time a planet takes to orbit depends on its distance away from the sun. And these laws are considered to be profound commentary on how we observe the night sky. The invisible structure of gravitational interaction eventually inspired Sir Isaac Newton and helped him derive his law of universal gravitation or gravity. It was not the apple that fell from the tree. No, it was work that Sir Isaac Newton thoroughly understood and had to develop calculus and algebra further to be able to help us solve physical science phenomena that we encountered in this class. So together, Kepler and Newton, they connect with things like force, concepts, and motion, and shows that the cosmos runs on predictable mathematical harmony. And in this week's module, we're going to use that same framework to interpret stellar and galactic motion, utilizing some of our citizen science apps like Stellarium. Because when a star wobbles, we can detect the pull of an unseen planet or object. And when we track, say, binary stars or the paths of comets, we're witnessing Kepler's work in action, echoes that order within the vastness of space. Now, what's interesting is that astronomy brings together really so many branches of science. In this week's module, we're going to combine orbital dynamics with electromagnetic radiation. That is, light influenced by chemical composition and magnetic fields to figure out a star's velocity, composition, and even distance. Then we can classify our stars. We use tools like the Hertzsprung-Russell diagram or the HR diagram to map these findings and chart the diversity of our night sky. This diagram essentially is plotting luminosity against its surface temperature that star is producing through a reaction and reveals patterns that tell us where a star sits within its life cycle. You see, most stars, including our sun, live on what we call the main sequence, a region defined mostly by mass. Mass shapes everything about a star, how it burns, how bright it shines, and how it eventually dies. Whether in a gentle fade or a spectacular supernova. And these phenomena are ones we can study right here on our online digital classroom. So I want to take you on a little bit of a star tour of the night sky and show you a few stars that I think are great examples to think about when you start handling your data for the HR diagram for this week's module. And let's take a look at a few of them. Let's look at Rigel, a blue supergiant right here. Rigel shows up on the HR diagram as being blue to white because it has a surface temperature of about 11,000 degrees Kelvin. And again, it's a blue supergiant found in the constellation Orion, and it burns incredibly hot and bright, thousands of times more luminous than our own sun. And when you see Rigel, you're looking at the life of a star racing towards its spectacular supernova end. We can also take a look at Cirrus, which is a double or multiple star, depending on who you are asking. And there is Cirrus right there. And we will zoom out just a little bit and show you that it is less blue and more white. And that is because it's has a surface temperature of about 9,900 degrees Kelvin. It's considered to be one of the brightest stars in Earth's night sky. Its intense color is actually coming from its high surface temperature, but it's a great example of what a main sequence star will actually be, slightly hotter and more massive than our own sun. And speaking of the sun, we will look at our sun, also known as Sol. And there she is, right there. Our sun is actually yellow. We can see that through a physical observation without even needing a app like this. Also, just a good line of recommendation is just don't stare at the sun without protective eyewear. But the surface of our sun burns at about 5,800 degrees Kelvin. And our familiar yellow main sequence star is not too big, not too small. It's just average in terms of brightness and temperature. This is considered a part of perfect reference point for students like yourselves to understand where we fit on that HR diagram. And sometimes the sun is used as a control in experimental design for those that study the night sky. We can take a look at another star called Arcturus, which is a red giant seen right here. And I'm trying to get the nice red look. But as I mentioned, it's red, but not quite red. We would call that more orange. And that's because it's burning at about 4,300 degrees Kelvin. And it's a giant star nearing the end of its life. It's got a cooler surface temperature, which gives also rich orangish hue, and it shows that our sun might look like billions of years into the future as it expands into a red giant. And then one of the other red stars is that of Betelgeuse. You can see that faint red orange right here, as that is burning about 3,500 degrees. It's considered to be a red supergiant, one of the largest visible stars, and its deep red glow is a visual sign of a cooling surface temperature. Betelgeuse will one day end in a brilliant supernova explosion when it hits its end of life. So when we talk about astral phenomena, we're really talking about the fusion of the ancient sky watching traditions with modern astrophysics. From electrostatics to gravitation, from particle physics to celestial mechanics, we've built a language to interpret the cosmos itself. So grab your stellarium, grab your notebook, and fire up your curiosity, and get ready to explore how starlight becomes science and how can we track the movement of our celestial neighbors that our planet Earth shares its neighborhood with. Because in this module, you're not just learning about stars, we're learning on how to read the universe as physical science phenomena occurs past our atmosphere. As always, if you have any questions about the module for this week, you can come and see me during my open office hours. You can send me an email, set up a video chat, or swing by my office. I am here to support you in your learning journey this semester.